Explorers, fur traders, history makers of Canada passed this way. 3 centuries later came scientists exploring other frontiers, making new history. This is the Ottawa River, and these are the Chalk River Nuclear Laboratories of Atomic Energy of Canada Limited, the birthplace of Canada's nuclear program. Here in 1945, the first atomic reactor outside of the United States came into operation. Here in 1953, work began on the development of electric power from the atom. And a few miles upstream at Rolphton, a site was chosen for a pilot plant. And the nuclear power demonstration station has been generating electricity since 1962. It was becoming clear that the traditional sources of power, such as the energy in falling water, would not be able to meet the fast-growing needs of homes and industries. But as the demand for power has grown, so have our skills in generating it. Today, we harness the internal energy of matter. There are many nuclear power plants operating in the world today. One of the largest is at Pickering, on the eastern outskirts of Toronto on Lake Ontario. Built and operated by Ontario Hydro, it consists of 4 reactors, which generate as much power as the entire output of Niagara Falls. Pickering's performance record is such that engineers and scientists from around the world come to observe the engineering, the computerized controls, and the efficiency of the fueling system. The uranium fuel comes in easy-to-handle 54-pound bundles, each with the energy equivalent of 250 cars of coal or 100,000 gallons of fuel oil. When you consider that one reactor contains 4,500 fuel bundles, you have some idea of its output. Sensors measure temperature and pressure at several hundred points throughout the reactor and feed the information back to the control room. A feature of the Canadian system is that reactors can be refueled while under power, an obvious advantage over those systems in which the reactor must be shut down while their fuel charges are replaced. The fueling machine is raised into the reactor vault from an underground loading bay. Each of 390 fuel channels is monitored once every 2 seconds. The computer determines which fuel bundles are due for replacement and sends instructions to the fueling machine, which homes onto the appropriate channel. The machine couples itself into place and inserts a new bundle. On the average, a bundle will stay in the reactor for a year and a half. A reactor is only a special furnace in the thermal generating plant. It produces heat. Cooling water flows into the reactor and over the hot fuel bundles and carries the heat from the fuel to a boiler. Water in the boiler is turned into steam. The steam drives a turbine, and the turbine drives an electric generator, which delivers electricity. The spent steam is condensed by cold water from a lake, a river, or the sea, and returns to the boiler. So the system is basically the same as in any steam plant with the same product, electricity. The difference is the reactor, where the heat is produced not by the combustion of oil, coal, or gas, but by the fissioning of uranium. Uranium, the heaviest element in nature, like all matter, consists of atoms. In the atom, a cloud of electrons whirls around a heavy nucleus. The nucleus consists of two kinds of particles, protons and neutrons. Nuclei of uranium are somewhat unstable, and from time to time one flies apart, fissions into two heavy fragments traveling at tremendous speed. Watching it again, we see that 2 or 3 neutrons also fly off, and that the heavy fragments collide with nearby atoms, setting them in motion, a motion we call heat. This is the heat we want to harness. But normally, this fissioning process occurs too seldom to give us a useful amount of heat. We must greatly increase the rate of fissioning. And here, the neutrons can help. For if a nucleus is hit by a neutron, it will fission, releasing more neutrons and heavy fragments, and producing more heat. But the neutrons are normally traveling too fast to cause sustained fissioning. The trick is to slow them down, to moderate their speed. A very good moderator is heavy water, a special kind of water containing atoms of heavy hydrogen called deuterium that are about the right size to slow the neutrons down without absorbing them. Now the slower neutrons can more easily contact other nuclei of uranium, causing them to fission, releasing more neutrons, which cause more fissioning. A chain reaction is set up. Plenty of heat is produced. So a Canadian nuclear reactor is essentially bundles of natural uranium fuel in a tank of heavy water. It is called CANDU, for Canada, Deuterium, Uranium. An important engineering feature of CANDU reactors is that the fuel is contained in separate tubes passing through the reactor vessel. The coolant, to take the heat from the reactor, flows over the hot fuel through these channels. In most CANDU reactors, the coolant also is heavy water, kept at high pressure. One of the several advantages of this system of separate tubes is that it permits on-power refueling. At Pickering, 2 machines operate in tandem. When a fuel bundle has served its time, a fresh one is inserted at one end, and the spent fuel is removed from the other. Fuel bundles removed from the reactor are easily and safely stored in a pool at the station. Within the spent fuel is potentially valuable plutonium. Although not economic to do so now, the time may come when it'll be worthwhile to recover the plutonium for use in modified CANDU systems. The radiation given off by the spent fuel causes a blue glow in the water, known as the Cherenkov effect. It has been forecast that by the year 2000, nearly half of Canada's electricity will come from nuclear power plants. An important feature of the CANDU system is that it uses natural uranium fuel, and Canada is one of the world's largest producers of uranium, with many deposits throughout the Canadian Shield. The ore is refined and processed into uranium oxide powder, pressed into pellets, and placed in zirconium alloy tubes. The tubes are sealed by welding. A number of tubes are joined together to make up a fuel bundle. Space between the tubes allows efficient passage of the coolant. We have seen that uranium alone does not produce the heat required to make electricity. Now let's consider the moderator used in the CANDU system, heavy water. Heavy water occurs naturally in ordinary water, but only at a ratio of 1 part in 7,000. To capture that small drop, a great deal of water must be purified and run through a series of processing towers. It is in these towers that the precious particles of heavy water are extracted. A molecule of ordinary water consists of 2 atoms of hydrogen and 1 atom of oxygen, the well-known H2O. The atomic structure of heavy water is almost the same, except that in the nucleus of each hydrogen atom there is an extra particle, a neutron. This makes it into a heavier form of hydrogen called deuterium. Heavy water's formula is D2O, and it is the relatively rare D2O that must be extracted from ordinary water. The method used in Canada's heavy water plants is the hydrogen sulfide process. Ordinary water with normal traces of deuterium flows down over a series of trays, while hydrogen sulfide gas passes up through perforations in the trays, mixing thoroughly with the water. The extraction depends on a special property of deuterium. If the temperature is high, it migrates to the gas. If the temperature is low, it prefers the water. So the gas and water are circulated through towers with hot and cold sections. Deuterium is extracted from the large flows of ordinary water and concentrated in the gas near the center of the tower. Then it flows to more towers for further concentration. In the last stage, the process is reversed, and the deuterium is drawn out of the gas into a small amount of water. As there is a slight difference in the boiling points of light and heavy water, the heavy water can now be extracted in standard distillation towers. Because of the magnitude and complexity of the operation, the end product is worth several $1,000s a barrel. Canada's heavy water plants produce heavy water to supply all of our own needs, with enough left over for shipment abroad to other nations. The Chalk River Laboratories, where it all began, still provide the scientific thrust of Canada's nuclear program. Here are some of the world's most powerful and versatile research reactors. Fuels and materials being developed for power reactors can be tested here under operating conditions of temperature, pressure, and radiation. The Chalk River reactors also perform the valuable function of producing radioactive isotopes, such as the cobalt-60, one of the most effective weapons in the worldwide fight against cancer. The ordinary cobalt-59, now being readied for insertion, will remain in the reactor for 1.5 to 2 years, and will then emerge as the radioactive isotope cobalt-60. Some of the work at Chalk River is pure science. It's not meant to have immediate application. It's a matter of extending the frontiers of knowledge in a way that eventually will benefit mankind. The Tandem Van de Graaff accelerator is an atom smasher that uses 13 million electron volts to accelerate charged particles, moving them in a narrow beam at speeds of up to 40,000 miles per second. The stream of particles is bent by a magnet and directed along separate lines in the target room. Scientists can observe the collision of the high-speed particles with the nuclei of different elements, and in this way learn valuable lessons about the nuclear structure of those elements. But much of the work at Chalk River is directed to more immediate problem solving. The contact between liquid and gas is studied in research to back up the heavy water program. and research is constant into improving ways of using nuclear fuel. A feature of the CANDU system is that it can be modified to accept different sorts of fuel. In the materials labs, researchers are looking for more efficient ways of using uranium and how to make use of the plutonium that is generated in CANDU reactors. The use of plutonium could greatly extend our reserves of fuel. In the accelerator physics branch, scientists are studying the possibility of producing neutrons on a large scale without the use of a fissioning nuclear reactor. Instead, they are working with a high current, high voltage accelerator. The challenge here is to create and contain very high energy beams. The higher the voltage before sparking takes place, the more successful the experiment. The digital counter is measuring that voltage. This is a long-term project and a significant one. The development of such a neutron source could open the way to the use of other elements as fuel for nuclear power reactors. One such element could be thorium, which is even more abundant than uranium in the Earth's crust. Like all research in nuclear physics, the accelerator program requires patience and perseverance. Scientists from many countries come to Chalk River for consultation and to work in what is described as a friendly environment for advanced research. There are other visitors too. Each year, thousands of tourists come to see new developments in science and engineering. There is an information center with scale models of facilities in the laboratories. And natural radiation is clearly demonstrated in a cloud chamber. Mechanical hands, or manipulators, used throughout the nuclear industry for safe handling of radioactive material, never fail to fascinate. A Chalk River product with important medical and industrial application is Cobalt-60, which is packaged and sold by AECL's Commercial Products Group at South March on the edge of Ottawa. The Cobalt-60, received from the reactors of both Chalk River and Pickering, gives off powerful gamma rays. The operators are protected from the radioactivity by a 3-foot-thick window filled with heavy oil. The main use of Cobalt-60 is in cancer treatment. Canada produced the world's first cobalt therapy unit in 1951 and has since sent more than 1,000 of these medical devices to more than 60 countries. Teletherapy works by directing beams of gamma rays at malignant growths. A single charge of Cobalt-60 in the operating head of a therapy unit is good for up to 5 years. Cobalt-60 has other uses. A cobalt source can be used in large-scale sterilization of medical instruments and supplies. This demonstration model shows how packages to be sterilized are passed automatically back and forth over, under, and around the central source of radiation. Yet another use of the isotope is in direct conversion of heat to electricity, to power such things as navigation beacons, which can function unattended for years. Another useful device manufactured by AECL Commercial Products is a pocket-sized but nonetheless fully functional research reactor. It's called Slowpoke, which stands for Safe, Low-Power, Critical Experiment. Slowpoke is a versatile instrument. It can be used in analyzing minute quantities of many different materials. Here at the University of Toronto, the Slowpoke is helping researchers analyze air pollutants. It can also be used for on-the-spot production of short-lived isotopes of different elements useful for research and for medical diagnosis and treatment. The university's Slowpoke is used for hundreds of irradiation experiments and tests. Radiation is a natural phenomenon. Some of it reaches us from outer space every day in the form of cosmic rays. Minerals in soils and rocks give off radiation. People and animals are, to a small degree, naturally radioactive. For 30 years, scientists of Canada's nuclear program have carefully measured that radiation and monitored the area around such man-made sources as nuclear research sites and power plants. These environmental scientists have used radioactive isotopes to study plant life and to follow food chains. They've studied the effect of heat on aquatic life. Over the years, they've gathered a substantial body of knowledge about the protection of the environment and people. Researchers of the Université de Québec at Trois-Rivières checked the effects of the outflow water from a nearby power station. This is the nuclear age, and atomic energy is a thread in the fabric of progress across Canada. In Vancouver, 4 Western universities are collaborating in the building and operation of a powerful large-scale accelerator that will produce particles called mesons. Its immediate purposes are to carry out advanced medical and nuclear structure studies. The Whiteshell Nuclear Research Establishment of AECL at Pinawa, Manitoba, has been in vigorous operation since 1963. At the heart of the site is a research reactor for testing fuels and materials for the power program. This is the world's only reactor that uses an organic oil-like substance as the coolant. The value of the organic coolant is that it can be used at a higher temperature and pressure than water. Material for testing is carried in a loading flask and inserted in a channel in the reactor where it is subjected to heat, pressure, and radiation. The laboratories at Whiteshell carry out detailed examination of materials exposed to radiation in the reactor. Facilities include chemical, metallurgical, engineering, and medical laboratories. Painstaking research is the basis of new advances in Canadian nuclear technology. On the south bank of the St. Lawrence near Trois-Rivières is Gentilly, Quebec's first nuclear power station. Completed in 1971, it has an output of 250,000 kilowatts. Nearby, Hydro-Quebec is building a second station that will have a capacity of 600,000 kilowatts. The core of nuclear engineering in Canada is AECL's Power Projects Group at Sheridan Park near Toronto. Here, the nuclear power systems for Canadian utilities and overseas customers are planned and designed. Engineers and technicians design and test components and deal with the many complex details of nuclear power systems. One group at Sheridan Park is concerned with the refinement of computer programs that monitor reactor performances and instruct fueling machines. Single-pass welding, computer-controlled and remotely observed by television, is another front of study. This technique is useful in confined areas that are radioactive. The joint is made without use of filling metal, using very high-level electric currents. In the labs at Power Projects, Full-scale prototypes of the components and sub-assemblies that will go into reactors are tested under simulated operating conditions of pressure and temperature. Once the design has been proven, the actual manufacture of all the parts, large and small, that go into CANDU plants is carried out by private companies. From its beginning in the 1940s, Canada's nuclear program has involved private industry as well as utility companies and universities. The reactors and their complicated components and almost all the other hardware that goes into a nuclear power station are built in the factories of companies in many parts of Canada. Canadian companies are also producing components and equipment for other countries. Our nuclear knowledge bank is constantly becoming richer, and it is drawn upon more and more frequently as the demand for nuclear power rises. There's no doubt that the demand will continue to grow. Forecasters predict a rise in Canadian power demand of 7% a year. Canada's power generating capacity will increase 7 times over the next 25 years. The demand would soon far exceed the supply, were it not for the availability of nuclear power. Electric utilities have played a major role in the Canadian nuclear power program, and the size of their role is rapidly increasing. Construction of new stations will continue for many years to come. Through the cooperative efforts of utilities, private industry, universities, and government, Canada has developed an independent, competitive, efficient nuclear power system. The nuclear age is no longer a distant dream. We are living in it.